Memory and data integrity involves detecting data corruption using techniques such as mirroring, parity, SecMed codes, checksums, and CRCs. Whenever you're doing data integrity checks, you end up with an arrangement like this. There's a data word, that's the data that you'd like to protect, and you perform an error code calculation of some sort on it. We'll get to those in a minute. And that results in an error code. The error code is a thing that gives you extra information so you can check it against the data word to see if the data word has been corrupted or matches the original data word. A terminology note, there's a thing called a code word, and a code word is simply the data word and the error code taken as a set of data. After you've computed an error code, you do something with the data, such as store it in memory or transmit it. While that data is in transit or in storage, things might happen to it. So later on, you recover the data word and the error code, and you try and figure out, is that data corrupted or not? It's possible that there's been some data corruption, and a typical fault model for this is bit flips. The idea is one or more of the bits in the data word or error code, so somewhere in the code word, there's been a bit flip that changes the value of the data from what you stored or what you sent into what you recovered. The whole point of data integrity is to make sure that the suspect data that may or may not have an error in it actually matches the original data. You do this by taking the data word, performing another error calculation, typically the same error calculation you performed in the beginning, and you match that against the error code. And you say, well, if the computation of the error code based on the received data word matches the error code that was also received, then most likely no memory corruption has occurred. The baseline for memory integrity efficiency is a random hash. Consider if you had a magic function that took the data word and scrambled all the bits optimally so that the error code was indistinguishable from a random value, completely unpredictable. Then in that case, what you'd get is that if you have a k-bit error code, there's a 1 in 2 to the k chance that you got unlucky and whatever corruption happened to the code word happens to result in a situation where the error code matches the data word. Think of it this way. If you took completely random data for the data word and completely random data for the error code and matched them, if the error code is k bits, by random chance, there's a 1 in 2 to the k chance they'll just happen to match. So the baseline performance for an error code is that completely random probability of 1 in 2 to the k. Perhaps surprisingly, you can do a little better than that for small numbers of errors, and that's where error code design comes in, and that's mostly what we'll be talking about. I should note that malicious faults require cryptographically strong integrity checks. For this tutorial, we'll assume a non-malicious adversary, in other words, just plain random noise, not a person or computer program trying to intentionally fool the error code. All the error codes we discussed are in fact quite easily fooled by a malicious adversary, so this is only for accidental faults, not malicious faults. The anti-patterns for data integrity are, if you have no checks on memory data, no checks on your program image, no checks on your configuration data, and your values in RAM and other data have no integrity checks, then you're subject to data integrity problems. In life-critical applications, that's a big deal because, as we'll see, memory values will be corrupted over time, and you have to account for that possibility. The other anti-pattern is not having end-to-end message checks. If you're sending messages on a network, especially a multi-hop network, the application layer needs to wrap its own integrity protection around the values it's sending because the data networks might not provide enough protection against corruption of values. Another anti-pattern is using checksums instead of CRCs. CRCs are much more effective than checksums in general and are not that much more expensive to compute.